So now let's take a look at certain parameters of the radiation characteristics that arise from the radiation characteristics of an antenna. Certain parameters, certain specification quantities that have certain numbers to it to determine different antennas, what are their characteristics are. So those parameters, specifically if you look at the radiation characteristics, they are listed as here: directivity, gain, efficiency, half power beamwidth, and effective isotropic radiated power. So quite a few of them, but we will take a look at one by one. And when we mean the first thing, when we mean by directivity, what it essentially means is this captures how much is an antenna is radiating in a particular direction compared to an isotropic radiator. So by what we mean by that is, if you were to imagine an isotropic radiator, that's going to radiate equally in all the directions. So it's going to be having a spherical pattern like this. So if I had, instead of the isotropic pattern, if I had a directional antenna, all that the directional antenna is essentially doing is squeezing this ball. Imagine this to be a stress ball. If you're squeezing this, then turns out that you are likely to radiate more in a particular direction than compared to this isotropic radiator. So this change in the power density, or rather how many watts per meter square, the power density meaning how many watts per meter square are you radiating in this particular direction compared to an isotropic radiator, is what we call as a directivity. So we give a number to it. For example, for an isotropic radiator, it is going to radiate equally in all the directions, so the directivity value is 1. So this is in linear terms, but in dB, if I were to convert it to dB, I'm going to be using 10 log 10 of the directivity in dB, and that becomes 0 dB. So if I say that the antenna is having a directivity of 0 dB, then we call it as an isotropic radiator. Now that the directivity is always with respect to the isotropic, we call that in dBi. We call that a special unit of dBi, meaning that many dB with respect to an isotropic. So for a isotropic antenna, it is going to be 0 dB with respect to an isotropic radiator. So the directivity is simply 0 dBi. If you had, let's say, a 20 dBi gain directivity, if you have directivity of 20 dBi, once you see an I, we know that that is going to be a directivity. The linear directivity that is going to be for this case is going to be 100. So in that sense, we are saying that it is going to be this directive antenna of having a directivity of 20 dBi is having 100 times more power density in a particular direction, in the direction of the peak gain, compared to an isotropic radiator. So that's what a directivity means. So in this case, this is going to be a directional antenna, and this is going to be an isotropic antenna. So the next parameter we're going to look at is what is called as the gain. Gain relates to how much is the power that you're going to radiate in a direction depending on with respect to the power that is accepted by the antenna. To understand that, let's see this picture here. Let's say there is a certain RF source that is feeding in a certain input power P in. When you connect that to the antenna terminals, there is a part of that power that is accepted by the antenna, and part of it can be reflected back. How much is it reflected back depends on the reflection coefficient of the antenna. The reflected is going to be P in gamma antenna square, yeah, where this is in linear terms. How much is reflected depends on the reflection coefficient. How much is accepted, in fact, is going to be 1 minus what is reflected times the input power. This is going to be the accepted power. This is going to be the accepted power by the antenna. And turns out that need not all the power that is accepted is going to be radiated. The antenna itself can have some lossy materials in it, and it can have some power that is absorbed power. This power is lost in the antenna. It is lost. So it is absorbed by the antenna because of resistive materials, or maybe made of some metals which are not very highly conductive. Even copper, for that matter, has a finite conductivity. It is not infinite, so there can be some losses there, and only part of the accepted power is leading to the radiated power. So gain in that sense is going to be written in G, directivity is written in D and is a function of theta and phi, whereas gain is going to be again a function of theta and phi. That means which direction are we looking at? It's going to be different in different directions. It's going to be a function of theta and phi, but then it is going to be related to how much is the radiated power in a particular direction to the ratio how much is it how much is the accepted power. And turns out that this gain is related to the directivity through a parameter what we call as the efficiency of the antenna. So the gain is proportional to directivity and is related through the efficiency. And when we say efficiency, it takes in what is the radiated power with respect to the input power rather than the accepted power, whereas gain is in the accepted power. This is how much is the input power. So if we go ahead and do the math, we will see that the accepted power in terms of the input power is 1 minus gamma A square. So we see that in terms of accepted power over the radiated power, which is our gain, this factor is going to be our gain. This is proportional to the efficiency is going to be proportional to 1 minus gamma A square. That accounts for the reflections at the antenna terminal, at the antenna. So the radiated power, the accepted power, as before we see that has both the absorbed and the radiated power. If the absorbed power is 0, that means there are no losses in the antenna. That means the efficiency, if the absorbed power is 0, then the efficiency is going to be 1 over gamma A square. Essentially, whatever is being accepted is going to be radiated. So the efficiency is dictated by how much the antenna accepts. And how much the antenna accepts depends on its return loss gamma A, the reflection coefficient gamma A. The other pattern characteristic that we are looking at, a half power beam width, is going to be dependent on the radiation pattern. Let's say for a directive antenna, the pattern is dependent on the angle. Let's say if here we are looking at a certain cut of the three-dimensional radiation pattern, it's radiating a high value in this particular direction, its maximum, and that directivity is, let's say, 15.48 for example. If I were to take that directivity and if I were to go 3 dB down, so what's special about 3 dB? We know that minus 3 dB is half power. So we want to see for what angle does this antenna receive half the power compared to the peak, and that angles are going to be these two angles where it's going to receive half, which is 15.48 minus 3 dB is going to be 12.48 dB. So that two values, the angles that where I receive that power, if I were to sweep that angular width, this angular width is what we call as the half power beam width. The width of the beam where the power is half, that's why you call it a half power beam width. The next one we are looking at is effective isotropic radiated power. Is if you were to feed in the antenna with a certain input power, how much is it effectively radiating? If I were to have an isotropic radiator, how much is, by having a directional antenna, I'm getting additional gain of G. Yeah? If I were to have an isotropic antenna, all the power that I would be able to radiate effectively is only the input power because it's radiating isotropically everywhere. Whereas when you have a directional antenna, this additional gain factor comes in, that I'm able to effectively boost what if I were to have an isotropic radiator. In essence, I would be effectively transmitting this much of power rather than this much. The gain of the antenna is treated as how much effectively, if I were to have an isotropic radiator, how much is the input power that I can effectively have. So because of the gain of the antenna, effectively we are having this much to be the effective power that is being utilized by the antenna for the radiation. Then comes the factor where if there are any losses in the system, like let's say cable losses or even antenna losses, the cable losses losses in the cable, that is characterized by the L. These L is the loss in the cable. We may not be able to get the complete input power at the input end of the antenna. There might be some losses in the cable, and that needs to be subtracted off. That is EIRP, the effective isotropic radiated power in a particular direction. Now, if we get the EIRP in a particular direction, and if we were to integrate that over the entire three-dimensional volume where the antenna is effectively radiating, then we get what is called as the total radiated power, or TRP. So we are essentially seeing the effective isotropic radiated power in a particular direction and integrating it over the entire 3D volume, and 4 pi being the solid angle of a full complete sphere where the integration is performed. This is going to be the total radiated power. The final quantity that we are going to look at is what is called as the effective area or aperture of an antenna. Is a equivalent area. It's an area factor. It's an equivalent area in millimeter square. That is in fact actually proportional to the physical aperture size of the antenna. But this effective area relates how much is the power density. The power density that when incident onto an antenna translates to the power that you receive at the terminals of the antenna. How much of this power density usually denoted by the letter W, how much is this power density, meaning watts per meter square, how much is that power density is able to translate to the received power in watts. So we multiply that by the area, which we call as the effective area of the antenna. So that effective area is related to the gain of the antenna by this expression lambda square G over 4 pi. This lambda square G over 4 pi is the effective area of the antenna. And in some sense it's also related to the physical size of an antenna for aperture antennas, where it is proportional to the physical size and it depends on the efficiency of the antenna. So bigger the antenna with a good efficiency, of course, bigger the size, then higher the effective area and more will be the received power for a given power density. So these are some of the radiation parameters that arises due to the radiation characteristics of the antenna, that will be a good gauge to compare two different antennas in terms of their performance metrics.